Okay, good evening, students. So today we'll do the topic potential and potential energy. So let me just remind you that if this is origin and this plus q charge is placed at origin, and I have this test charge plus q and I'm bringing it from infinity to this point P. So this is the direction in which electrostatic force is acting. So this plus q will be repelled. So that's the direction of electrostatic force, but this is the direction of applied force. So they are exactly equal and opposite, and acceleration is 0 here. So this way the work done by the external force or applied force, you can also write external, so work done by external force will be stored in the form of potential energy. Potential energy of Q, potential energy of this test charge. So whenever we do the work against the electrostatic force, that work done is stored in the form of potential energy of the charge. So even if we do it like we have the electric field here, and field lines, they start from positive and they end at negative. So there can be both of them, there can be only negative, there can be only positive. But this is uniform electric field, and that's the direction of electric field. Now I have a dipole. So this is dipole is equal and opposite charge, it's a pair of charges. So it's minus q and plus q. And the direction from minus q to plus q, that's the direction of dipole moment. Now let this angle be theta between the electric field and the dipole moment. So this is the electric field, and we have the dipole placed in external field. So I want to find out here potential energy of dipole in an external field E. So what will be the energy of the dipole? So obviously this positive charge will, what will the force? F is equals to QE, right? So the force on the positive charge will be in the direction of electric field. So in the direction of electric field. So you have, this will be the direction of force, electric force on plus q. And This will be direction of electric force on minus q. So equal and opposite forces and along different lines of action. So they will form a couple and there will be rotation. So there will be rotation. And this way it will rotate. This whole dipole, it will rotate. And this is the axis. So it will rotate. And this plus Q, this P will align with E. This P, dipole moment, will align itself with E, and then it will be the equilibrium stage. So here, as the forces are equal and opposite, there is no net force, but as they are along different line of action, so we will have the torque. And that torque is given by tau equals to P cross E. We have done it in chapter 1. So this torque will tend to rotate the dipole unless P is parallel or even. So this P will be in this direction. Even when P and E are anti-parallel. So here they are anti-parallel, theta is 180 between them, and here they are parallel, theta is 0 degree. So this torque will tend to rotate the dipole unless P is parallel to E or P is anti-parallel to E. Now, here also, this the job of always, whether it is gravitational force, electrostatic force, spring force, they are all conservative forces. Always, they act in the direction of decreasing potential energy. So students, remember this rule. The direction of conservative force, they always act in the direction of decreasing potential energy. So here, this is the direction of electrostatic force. So it means in this direction, potential energy will decrease. Right? So leave this charge over here, remove the external force. So this charge will move this side back to infinity, and this potential energy over here will convert it into kinetic energy. And for conservative force, the total mechanical energy of the system will be conserved. That is, kinetic energy plus potential energy is constant. So this whole potential energy will be converted into kinetic energy. So that is the job of electrostatic force. It will act in such a way that it will decrease the potential energy of the particle. And same is the case here. This tau will act, it will try to means align, or anti means parallel or anti-parallel, this E and P, this is what tau will do. So this is what the electric field is doing with the dipole in this direction. So we have 2 tau, like we have 2 forces here, we also have 2 tau here. So this tau will align it P or anti-parallel to E. Okay. Now if we write this is what we are going to drive, we know it, that we have done it already. So this U, this is the relation that we are going to derive. U is equals to minus P dot E, and tau is equals to P cross E. So tau is the force and U is the potential energy, and this is a function of theta. It depends on theta, scalar quantity. Now the tau, due to the electrostatic force, electric force will act in such a way to reduce the potential energy, whereas tau external means that we are applying will act against tau E. Both are equal and opposite, just like it was here, and work done will be stored in the form of potential energy. So work done by external force will be stored in the form of potential energy. So we have 2 kind of torque here. So this is the direction of tau E, this electric field. So it will bring this rotated in this direction. Now this way potential energy is decreasing, and I want to rotate it in this direction. So tau external will act in this direction and increase the potential energy against the field. I will be rotating it against the torque of the electric field. This is tau external. So this is the whole concept about, students. So fundamentals are more important, and derivation it's pretty simple. So due to the torque, this will, so let suppose an external torque. So suppose this external torque is applied such that it is equals to tau electric tau provided by the electrostatic force, and tau external rotates the dipole in the plane of paper from angle theta naught to theta 1. at same condition, students, infinitesimal. So here also I was bringing it at infinitesimal small speed such that acceleration was 0. And even if you have a ball on the ground here and you are raising this ball to height h, so you need to raise it with infinitesimal slow speed. Acceleration is equal to 0 means F external must be equal and opposite to gravitational force. Then this work done by the external force will be stored in the form of potential energy of the ball, and that is equals to mgh if this height is h. So students, whether it is this case, whether it is this case, or whether it is this, so that's the case everywhere. So these two torque are supposed to be equal, and it rotates from, so I'm rotating it, I'm taking it this way, so both the forces are equal. Okay, otherwise if I apply only this force, so it will move, with such a speed, so I'm taking it at infinitesimal slow speed with both the forces equal, acceleration is 0. So without angular acceleration at infinitesimal, at an infinitesimal very very low angular speed, and without, and angular acceleration is 0. So no angular acceleration, and this is infinitesimal, this angular speed, and that's also constant because this angular acceleration is 0. So what will the total amount of work done by the external force? Therefore the total work done by torque external is equals to W. So students, another point is all these forces, all the conservative forces, when they act, they are variable forces. They are always variable, they are not constant. So work done by the variable force. So if it is a constant force, then it is F dot D. But when it's a variable force, then the work done is equals to F dot dr, and this is R1 to R2 position. So here also this force, it depends on theta, and you know it very well that these forces are, look here, this force depends on the distance between the charges, isn't it? Coulomb's force, electric force, that is equals to K Q1 Q2 by R square. So if you are increasing or decreasing this distance between the charges, then this will be different. So you are bringing near, so at every point this electric force is changing, and also the applied force or the external force is also changing. So the work done will always be in the integral form when this is changing. So now here I have torque. So how will I give it? So tau external into d theta. So it will positive work because I am doing it in the direction of the displacement. So the displacement will be in this direction, okay, and external force also in this direction. So both are in the same direction. So work done will be positive. And this theta 1 to theta 2. So now what is this tau? So this tau, of course, it's so this will be the magnitude only. Now what tau is? Tau is equals to P cross E. So what the tau will be equals to? That is equals to theta naught to theta 1. So I can take it theta 1 to theta 2 or theta naught to theta 1. So that's the same thing. And tau is equals to PE. What will the magnitude without direction? So that is PE sine theta. So theta is the angle between P and E. So let me write the magnitude of tau. That is PE sine theta d theta. So that's equals to PE is constant, will come outside. And what is the integration of sine theta? That is minus cos theta. And theta 1 to theta naught. So that will be equals to PE. So obviously this is negative, so this minus this is what you will get at the end. Okay. So the negative sign, if you put final minus initial, so negative sign will make it initial minus final. So this work done against the external force, this will be stored in the form of potential energy of the system. And of course, it's a function of theta. Now students, it is our choice where we are taking the potential energy as 0. It's our choice. See, here in this case at infinity, I am taking the potential energy at 0. Here at the ground, I am taking potential energy at 0. So we fix the potential energy at 0 at appropriate place. Okay. So here I'm taking this potential energy to be 0 at pi by 2 radian angle. So that's what you can write it as theta naught also. So theta naught is equals to pi by 2 I am taking. So here at this particular angle, the potential energy is 0. That is my assumption. That is what I am assuming. So then the potential energy, this potential energy which depends on theta, that will be equal to PE so I am taking this theta naught as pi by 2. Okay, so P and E. So what I am taking, let us see in the figure from where I am taking this angle between P and E is theta. So this is the angle between P and E. This is theta. And I am taking it to be 90 degrees, students. 90. Yes. So I am taking this P is 90 minus Q to plus Q. This P, direction of P is minus Q to plus Q. This direction of P I am taking. So that's P. This is the direction of P minus Q to plus. And this is the direction of electric field. So this angle is pi by 2 radian. And here I am assuming that potential energy is equals to 0. At this configuration, potential energy is 0. Remember, I was telling you, you started, suppose from here, this was the direction of P, this was your E, and you were taking it in this direction, and at this position U equals to 0. So it means U was negative over here. U was negative. And here it will further be more positive. So negative to 0 and more positive. Right? So at theta naught I am assuming the pi by 2. So cos pi by 2 minus, and this theta 1 be, let this angle be theta. So this I have taken as pi by 2 here, and this I am writing as theta. So I am rotating it actually from here to here. I started from this point. And I am rotating it in this direction. So this is my theta naught, and this whole angle is theta 1. Okay, so this was my initial position and this is my final position. This whole is theta 1. So of course I am rotating this against the electric field, so I am increasing the potential energy. So right from here, if I rotate it from here, I am increasing the potential energy, and here the potential energy reaches 0. That is what I have assumed. So it was negative and I was increasing it because I was working against the electric, the tau external, the rotating force was against the, so this was the direction of tau electric, conservative force. I was working against conservative force. So when I work against conservative force, the potential energy increases, and it is increasing, and it reaches 0, and it is further increasing, because this is tau external and this is tau electric field. So students, understand this concept. This is very easy to understand, not that much difficult. And this is my cos theta. So this is what my potential energy is. And further, this potential energy will be equals to, so what is cos pi by 2? That is 0. So PE 0 minus cos theta, and U equals to minus PE cos theta. So what is PE cos theta? That is P dot E. So this is what we were to drive, that U is equals to minus P dot E. Students, very important concept that come in exam is stable equilibrium, unstable equilibrium, and where the energy is 0. So let us understand the concept. Tau is equals to P cross E, and U is equals to minus P dot E. Let us see when theta is equals to 0, theta is equals to 90 degree, and theta is equals to 180 degree. Means theta is equals to 0 means this is P and this is E. Theta equals to 90 degree means this is E and this is your P. 180 degree, this is your E and this is your P. Okay. So what will be the value of tau and potential energy at these angles? Okay. Now theta is equals to 0. So this is equals to, so if I talk about the magnitude only, this will be PE sine theta, and this will be equals to minus PE cos theta. So everything depends on sine theta and cos theta. So at 0, sine theta is 0. So tau is equals to 0 at this point. There is no force acting. No force means no torque, no rotating force. Yes, both. No external, no electric force. So basically I am talking about the electric here, electric force, electrostatic force. The tau is 0. No electrostatic force is acting over here. So when there is no force, then I call it equilibrium. Okay? No force means equilibrium. Now, this is theta equals to 0. So what is u? U will be equals to minus PE. Okay, fine. Now at 90 degree, tau will be equals to, magnitude of tau will be equals to PE, sine 90 is 1. Here, we have already set potential energy to be 0 when the angle between P and E is 90. So this is what we have set up all by ourselves, our assumption, and put cos 90, 0, so U is 0. And at 180, what will be tau? So tau will be equals to, what is sine 180 degree? Sine 180 is again 0. So this tau is 0. This is again equilibrium. Equilibrium at both the places, but which one is stable and which one is unstable? That will be told by the potential energy. It will be stable equilibrium where potential energy is minimum. Let us see where the potential energy is minimum. At this angle, cos 180 degree. Cos 180 is minus 1. So minus PE into minus 1, and that is equals to plus PE. So here plus is more and negative is less. So here U is minimum at this angle. And here U is maximum. So that is why where the so this equilibrium will be stable. This equilibrium is stable because U is minimum here and U is maximum here. So this is unstable equilibrium at this angle. So the equilibrium is stable and equilibrium is unstable. There is no equilibrium over here. No equilibrium. Why? Why no equilibrium? Because tau is not equal to 0. So the dipole will be moving. And that is why in the beginning I told that external force will keep on acting. That's where we started with, that tau external or tau E will act till first thing till t is equals to 0, second thing, or t when P is parallel to E and when P is anti-parallel to E. So at both the places we have the equilibrium, tau is equals to 0. But this is a stable equilibrium because their energy is minimum, it is in negative. So you know this 0, this positive, this negative. So negative is lesser, right? So this is the minimum. So I hope you have understood it. Very important concept. And you will have definitely a question in your exam, might be objective question also from this concept. And you can also do example 2.6. So we have a molecule of substance that has a permanent electric dipole moment of magnitude. So you have the dipole moment of magnitude transfer minus 29 coulombs meter. So units, yes, okay, P is equals to 2AQ, so 2A units meter and coulomb, so coulomb meter. A mole of this substance is polarized at very low temperature by applying a strong electrostatic field of magnitude. So this is the electric field that you are providing, transfer 6 volt per meter. So molecule of a substance and 1 mole of this substance you have 1 mole, and this is the electric field that you are applying, and the direction of electric field is suddenly changed by an angle 60 degree. So delta theta is 60 degree. So direction of the field is changed. So this is the change in electric field. Estimate the heat released by the substance in aligning its dipoles along the new direction of the field. So definitely they will be in stable equilibrium when they will align themselves. So P and E were aligned, but now direction of E was changed by 60 degree. So that is why this all the P, so this was the direction of suppose E, and it is changed by 60 degree. So this is your new. So initially the dipoles were lying in this direction, they were in stable equilibrium. This was your P, so this was your E, they were aligned, theta was 0, stable equilibrium, and this is plus Q, this is minus Q. Now this dipole will align itself, it will move in this direction, okay, and will align it in this direction. So they all will rotate by 60 degree to reach the stable equilibrium, because this tau electric force will act on them and it will reduce their potential energy. Okay. So estimate the heat release. For simplicity, we are assuming 100% polarization of the sample. So all the sample is polarized. Now, so we have to find the heat release during this. So dipoles will align such that P is parallel to E. So there will be in this process heat release, and you need to tell how much is the heat released in doing this. So heat release, potential energy was decreasing. So this potential energy was changing into heat and kinetic energy both. Okay. The dipole moment of each molecule is this much, and how many molecules you have? You have 6.02 into, so let us take for simplicity 6 into 10 power 23 molecules were there with this dipole moment. What is the total dipole moment? Of the molecules. So this is a vector quantity, but all the dipoles were in same direction. So that is why, as they were in same direction, so they will be added up. So this was of one of the molecule. So let it be P dash for one molecule. So this is for 1 mole now. So for 1 mole, this P will be equals to 6 into 10 to the power 23 into minus 10 to the power 29 coulomb meter. Right. So one molecule has this much of dipole moment, and these many molecules will be multiplied to get the total dipole moment. And this comes out to be 6 into 10 to the power minus 6 coulomb meter. Now what was the initial potential energy? Initial potential energy is minus P dot E. So that is equals to minus PE cos theta. So what was the angle between? So E was here and P was here. So the angle was 60 degree. So put the value of P, 6 into, this is the total P now, 6 to 10 to the power minus 6 into what is E, 10 to the power 6 volts per meter. That's your E. What is cos theta? So initially when they were not aligned, so both were in same direction, E and P. So initially the angle was theta, and then the theta was changed to 60 degree. So initially it was 0. So cos 0. That is equals to, now this plus 6 minus 6 will cancel out. And this is minus 6 joules. So this was the energy when it was aligned. So of course it was negative. So it was negative minus PE, stable equilibrium. When they were both aligning, angle was 0. Now, final potential energy. I have changed the angle theta to 60 degree of the electric field. So now, UF is equals to minus P dot E, that will be equals to minus 6 into 10 to the power 6. So P is same, E is also same, but the angle is changed. Now the angle is cos 60 degree. What is cos 60 degree? 1 by 2. So half of this. So half of this is minus 3 joules. So how much is the change in potential energy? That is UF minus UI. Final minus initial is the change in potential energy. So final is minus 3J minus 6J, and that is equals to minus 3 plus 6, and that is plus 3 joules. So students, that's the change. So minus 3 to plus 3. So minus 6 to minus 3. So this was the energy initially, UI, and this is the energy final, minus 3 joule. So it means the change is plus 3 joule was added to it. So this plus 3 joule energy is lesser now. Okay, this is lesser by plus 3. So loss in potential energy. That is also same, greater minus smaller. We know that this is greater minus 3, and minus 3 minus 6 is, that is the loss. So it's the same thing, greater minus smaller. Loss in potential is 3 joules. And this is the energy released. This is the energy released by the substance in the form of heat. During the alignment of the dipoles in this direction. So E was changed, and then P, yes, it was also supposed to be in this direction for the stable equilibrium. So students, that was the topic, potential energy of a dipole in an external field. I hope now this topic